Welcome to Chemistry 111. We'll be finishing up Chapter 7, starting Chapter 8 today. I'm not sure how far we'll get into Chapter 8. Quick reminder, next week it's fall break. With that in mind, we will not have lab next week. However, it'd be cool if you could turn in your lab reports before the fall break gets started. So I have something to knock out, put some easy grades in, and try to correct you before we get too far into the Lewis structures and all that jazz. So please try to get your lab reports into me next week sometime before you go. Okay. Yeah. We had just finished last class looking at various different simple situations using the molecular orbital theory to look at various different simple diatomic gases. We put the electrons into the bonding orbitals first, then filled in the anti-bonding orbitals. And the bonding orbitals and anti-bonding orbitals canceled out based on how many electrons were each one. From there, we could determine essentially what was the bond order, or essentially what type of bonds are present. It was kind of a little confusing to some extent, but we saw, like, obviously hydrogen, how it appears in nature, would have a bond order of 1. Helium diatomic would not exist because it would have a bond order of 0. And some of these guys had some combination of a bond order of 1/2, making them semi-stable possible structures. Now, in itself, right here, looking at this is not super useful, but we can use this to look at row 2 elements. When we move on to row 2 elements, we get out of the S, and we now have access to p orbitals as well. So it's going to be similar, except the p orbitals, since there's 3p, we can have several different types of overlap. We can have the p end on end, which is just going to be like an s orbital. So you're going to form a sigma, a bonding orbital, and a sigma star, the anti-bonding orbital. But because of the p to p, if I do up and down or side to side, we get the pi overlap. So we end up generating 2 new types of bonding and anti-bonding orbitals of pi and pi star, the pi bonding and the pi anti-bonding. So what we see here is that right here, here's the s orbitals overlapping into the sigma and sigma star. And here's how the 3 p's would end up overlapping into the sigma of the p, the pi of the p, pi star of the p, and the sigma star of the p. And we can start filling those in the same way. Low to high would fill in all the electrons low to high and would end up generating what is the bond order of various structures. Now, there's one more tricky part, but I'll never, ever call you on. I doubt I'll even really test over this because we're going to have chapters 6, 7, and 8 on the next test. So at best, at the very worst, this will be like 1 question at the worst. But because these diagrams will always be generated for you, you won't have to worry about this weird part. That due to some overlap between the 2s and the 2p, there's a destabilizing effect. So that one orbital shoots up in energy in comparison to the other. So that the sigma goes down in energy and this sigma goes up in energy. And this typically occurs in the boron, carbon, and nitrogen. But in oxygen, fluorine, and neon, this effect is too small for the switch to occur, so you won't see it. All this will mean is that when we look at the diatomics of these guys, you're going to have, it's going to be arranged slightly differently. But so, MO theory will explain the structures of some of these guys. But we can also use MO theory to actually predict magnetism. Magnetism is caused by the electrons being either paired or unpaired. Whenever we have unpaired electrons, a molecule is magnetic, and so we call it a paramagnetic compound, which means if you put a magnetic field on it, it becomes attracted to it. Whenever all molecules are paired, they end up being diamagnetic, which means they end up being repulsed. So worst case scenario, I either ask you a question about bond order, or maybe I ask you a question about magnetism, if I ask you even a question at all over this on the test. So I wouldn't worry too much about this. But so let's look at this. We see down here, boron, diatomic. Each boron would have 3 electrons, so a total of 6. So we'd put in 1, 2, 3, 4, 5, 6. So what do we actually see? A bond order of 1 between a boron diatomic, if this were to exist. And would this be magnetic? The answer is yes, because we have 2 unpaired electrons. If we have carbon atoms goes from each one with 4, so a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And what we end up having is, so sigma and sigma star cancel out, a bond order of 2. Once again, we don't really see just a diatomic, but we do see carbon molecules. Graphite and diamond are made up of large-scale carbon atoms, lots of carbon atoms. And I do believe diamond is indeed diamagnetic. There's no magnetism present in diamond. It's actually. Now nitrogen. Nitrogen we do see. N2 we do see. Each nitrogen has 5, so a total of 10. So we put them in. Sigma, sigma star, those cancel out. Pi, pi, sigma, and 0 electrons in the anti-bonding orbitals. So what does that mean bond order wise? 1, 2, 3 bonds. 1 sigma and 2 pi. Just like we learned about last class. When we learned the difference in sigma and pi, we have 1 sigma and we have 2 pi. And what about nitrogen? Nitrogen ends up being diamagnetic. So this is repelled by a magnetic field. Now we start to do the same thing with oxygen. Notice oxygen, we have the flip. Instead of being 2, 1, we have 1, 2. But oxygen, we have 6 electrons each, so we have to put in 12 electrons. 1, 2, 4. Those cancel out. 6, 8, 10, 12. Now, because of this being p orbitals, we see these are unpaired. So let's break it down. Bond order 2, so 1, 2, 3, minus 1 is 2. So how do we imagine oxygen? How do we typically draw oxygen in a Lewis structure? We would say the double bond, a bond order of 2. Now, because of the weirdness of it being paramagnetic and unpaired, there's actually another structure for oxygen that exists that we deal with that has both oxygens having a radical on it. And there's a singlet version and a triplet version of oxygen, and that has to do with why oxygen is so reactive, that it actually forms this radical version, because it has these two unpaired electrons. And so oxygen acts really weird, and we can kind of explain oxygen's weirdness through this MO diagram. F2, we have now 14 electrons to use. These get paired up, so the pi and the pi star are both filled. So the net bond order is just 1. The bond order is just 1. As we see F2, we would not expect F2. F2 only has 1 bond. We only want to make 1 bond to fluorine. And of course, one last situation, neon 2. Each neon would have 8, add up to 16. We put that in there. All the bonding cancels with all the anti-bonding. We have a bond order of 0. And so we end up having a non-existent molecule. Neon is not a diatomic. It is not a diatomic because it's not stable as a diatomic. But now we see bond order of 1 for fluorine, bond order of 2 for oxygen, bond order of 3 for neon. Just like we would have drawn for a stable Lewis structure. Now, the final thing that can be done with this, all that was just, oh, we're doing diatomics. But really, the bread and butter of this is putting these guys together and trying to understand the overlap of heteronuclear compounds. So meaning atoms, 2 different atoms come together, 3 different atoms come together, and trying to understand the bonding structure of these 2 atoms or 3 atoms. So we have to add in all the electrons from each atom and put them in this diagram. Now, in certain heteronuclear compounds, not all orbitals will overlap. Like an s orbital can't pi bond. When that happens, we get non-bonding orbitals, which will not contribute to the bond order. They do not split into bonding and anti-bonding. They just stay the same. So the 2 examples I have here, HF, I'll start with HF. HF is just going to bond from the s orbital into one of the p orbitals. And so an F with having 7. So we put 2 electrons into the unused s, non-bonding, 2 electrons into the sigma bond, and then that's 6, 8. So basically, what is the HF structure? HF is a sigma bond between the H and the F and 3 lone pairs on the F. Or lone pair that are, these guys are non-bonding electrons. Now, NO, this one is actually way more interesting. Try not to sneeze. NO, so N would have 5, O would have 6. So a total of 11 electrons to use. 11 electrons to use. So we're putting in 11 electrons. We put them in the S, 1, 2. There's the sigma star, 3, 4. We start putting them in the sigma from the P, 6, 7. Well, let's say 5, 6, 7, 8, 9, 10. And we have to put one electron into the pi star. So we have one unpaired electron in this structure. One unpaired electron. The bond order of this guy would be somewhere between, so we had bond order would be something like 2.5. 2.5. So what does that mean? I want to show you this. So let's do this like we would do a Lewis structure. Let's do this like we do a Lewis structure. So you would have N, you'd have O. You have 11 electrons. There's 2. I would put 3, 4, 5, 6, 7, 8, 9, 10, 11. I would erase one of these to put it into a double bond, and that's where I have to stop. This guy has 7. This guy has 8. I cannot go any further because if I make another double bond, I end up putting, if I make another double bond, I'm going to end up with 9 electrons on the nitrogen, and we're not allowed to do that. So what do we have? We have essentially a bond order between 2 and 3. It's end up that lone, so that radical electron actually participates a bit in that bonding to give it that 2.5 bond lengths. But we see right there a radical electron, entirely predicted by looking at the MO diagram. Now, we can do the same thing with, this is the last slide, with CO and CN. CO and CN minus. Doing the CO structure, you can see what this would look like. We have overlap with the S's, P's. I'm going to skip and just do the redraw this. So just doing with the valence electrons. I'm going to just do it with the valence. 2s. Going to go da-da-da to our sigma. Da-da-da. Sigma star. Then we have our P's. 2p. Sigma. Pi. Pi star. Sigma star. Okay. Now, C has 4 electrons in the valence. 1, 2, 3, 4. Oxygen has 6 in the valence. 1, 2, 3, 4, 5, 6. So filling the electrons in. 1, 2, 3, 4. So we have a total of 10 we need to use. 5, 6, 7, 8, 9, 10. Since these guys will almost always cancel out, what is the bond order of CO? The bond order of CO is 3. 2, 4, 6 divided by 2 is 3. There's no bonds in the anti-bonding. If you draw the Lewis structure, you would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what would you have to do? You would have to erase a lone pair there, erase another lone pair. Now we have 8 and 8. So the Lewis structure of CO is essentially that, is a triple bond between the carbon and the oxygen. If you were to count formal charges on this baby, formal charges, you would actually put a formal charge of negative on the carbon, positive on the oxygen, which is not super stable, but them's the breaks. That's what you got. But that's why carbon monoxide is so dang reactive. You have a negatively charged carbon that wants to stabilize itself. So it's going to attack anything that's positively charged and stick to it. That's why carbon monoxide is so damn deadly when you breathe it in. It's going to bind to the iron in your hemoglobin. It's going to bind stronger than oxygen is. And it's going to bind so strongly, it's going to be hard to kick it off again. So much so that oxygen, the beauty of it is it can bind to the iron and then leave when it needs to leave so we can get the oxygen to the cells. If you have carbon monoxide binding to the iron and not wanting to leave, like a bad house guest, you essentially have dead blood cells that aren't useful for anything. That's why carbon monoxide can be very deadly. I'm going to skip cyanide, but basically it's the same thing. You would have 4 and 5. A negative charge makes 6. You'd fill it in the same way. Cyanide would end up being the same darn structure. But as I said, I'm not even really sure if I'm going to test over this stuff. So not going to worry too much of this right now. Don't mind the change in scenery. I have to quickly re-record a small little bit of the Chapter 8 beginning because it got screwed up. Okay. Chapter 8 deals with chemical reactions and aqueous solutions. Basically, we're getting into a little bit of the math, but we're actually starting to talk about how the elements mix, not just about what is making up a compound, but how does that compound now react? The big thing here is a chemical reaction. It's the main thing we'll be talking about. Let's pretend we're all stupid and we've never seen this before. A chemical reaction is the conversion of one substance, which we'll call the reactant, to another substance, which we'll call the product. The reactant could be an element or it could be a compound. The basic thing is it is something that's going to be converted into a new compound or element. The product is just the compound or element that will be formed. So a simple reaction here is 4 iron solid and 3 oxygen gas go to yield 2 iron oxide solid. 2 iron 3 oxide. So when we see these reactants, we're often going to see these little subscripted letters like S, L, G, or AQ. They're going to be the phase that the reaction is taking place. S for solid, G for gas, L for liquid, and AQ for a special type called aqueous, which means to be dissolved in water or aqua. Now, you note here that despite the conversion, the total amount of iron atoms will be the same. There's 4 on the left, 2 times 2, 4 on the right. There's 6 oxygen atoms on the left, 2 times 3, 6 on the right. We cannot change the subscripts here, so we have to add what's called a coefficient to balance this. Now, how can we tell a reaction is taking place? There will be certain little hints. You will sometimes see a change in color. Sometimes see a production of light, like when we burned magnesium. You might see a formation of a solid where there was just 2 solutions. Formation of a gas, 2 solutions. Or the absorption or release of heat when things are mixed. All these are good hints that reaction has taken place. When it comes to balancing a chemical reaction, we want to make sure that everything is on the same on both sides of the reaction arrow, that we have the same number of atoms of each element. And that's the basic gist of it. We cannot change the subscripts, as I said. We can only change the quantities of a given compound. So we can't make O from O2. We have to use O2 as a diatomic, so we have to balance everything else. We're just saying when we balance it, all we're saying is that we need another atom of this, another molecule of this in order to make it work out. So we'll balance these chemical reactions by putting coefficients in front of the balanced chemical equation. In this case, we have aluminum and iron oxide goes to iron and aluminum oxide. We have 1 aluminum on the left, 2 on the right. 2 irons on the left, 1 on the right. 3 oxygens on the left, 3 oxygens on the right. The easiest way to balance this is if that's 2, I double that. If that's 2, I double that. And the oxygens can just stay the same. And with that, we'll return you to the normally scheduled talk. Here's some examples of practice. Shouldn't be too hard. There's a trick to each one, though. So the first one is I say try to balance copper first. I say copper plus there's 1 copper on the left, 1 copper on the right. And I go, okay, that's good. There's 2 oxygens on the left, 1 oxygen on the right. So what do I got to do? I got to double the CuO. I can't just double the oxygen. I have to double both because it's copper 2 oxide. I can't if I made it CuO2, suddenly that would be copper 4 oxide. And I can't change the component of the compound. So when I double the CuO, I have to go back and double check. So now that I've doubled Cu, I have to double the copper again. So. Well, I'm saying you can't really have a fraction. You could, but it's not the best. You'd say Cu plus 1/2 mole of O2. Let's do this. So we'd double everything. You double 1, you get 2. You double 1/2, you get 1. You double 1, you get 2. There's our actual thing. So there's our actual thing. Now this one is a combustion reaction, a pretty common type of reaction. A combustion reaction, as we'll see in a slide or two, involves the burning of compounds in order to produce CO2 and H2O. We're burning a hydrocarbon to form CO2 and H2O. One trick in these structures is to always balance the carbon and the hydrogen first. Balance the oxygen last, because oxygen will appear in 2 different compounds on the product side. It doesn't always appear in 2 compounds on the reactant side, but it will always appear in 2 different compounds on the product side, which will make things a lot harder. Always balance the oxygen last. So I'd say there's 1 carbon, 4 hydrogens, 2 hydrogens. So the first thing I would do is I would double the hydrogens. So right now I would be looking at drawing a big CH4O2, those 2, CO2 and 2H2O. Let's see. My head's in the way. Whoa. Okay, so that's where I start with. The next thing I would do, so I would try to balance. I balance the carbon, I balance the hydrogen, I have to balance the oxygens. 2 oxygens, 4 oxygens. 2 oxygens, 3 oxygens. We are stuck. We have an odd number of oxygens on the left, an odd number of even number of oxygens on the right. So I would have to double the CH4O, which is methanol. That's going to mean I have to double this, and I have to double that. So I double it. So that's 4O, 8O. I have 8 oxygen on the left, 2 oxygen right there. So I need to add another 6 oxygen. So I'm going to change that to 3. That's going to give us 6. But the trick with all combustion reactions is we always want to balance the carbon and the hydrogen first. The carbon and the hydrogen first, and then we can fix it. And the last one, it's a weird one. Magnesium sulfate plus iron sulfate plus magnesium goes to magnesium sulfate and iron. Here's a nice little trick. Whenever you got like an oxyanion or something like that, where it does not change, we have a sulfate on the left and a sulfate on the right. You can treat the sulfate as just one unit. You don't have to break it down into sulfur and oxygen. I have 2 sulfurs and 8 oxygens on the left. You can say I have 2 sulfates on the left and 1 sulfate on the right. So I would have to double the magnesium sulfate to get the right number of sulfates. And then I would triple the amount of iron. So, yes. So, you have 2 sulfates. 2 sulfate. No, so you don't need to worry about the oxygens. What you could just say, literally, for this one, I'll just click the thing. You can literally say, leave the sulfate together. So I'm going to just double the amount of MgSO4. And then I double the Mg. So I matched up the Mg. Now, the last step, I'm going to just triple the amount of iron to get that to work. So I can leave the sulfate as one unit. I can leave the sulfate as one unit instead of trying to balance sulfur and oxygen both. Because sulfate is left unchanged from left side to right side, we can make our lives a lot easier. Okay. One of the things we'll do in this chapter is learn some reaction types. If you can recognize these common reaction types, you can learn a little bit about and predict what the products are and understand what's actually going on. Eventually, we will get to talking in depth about 3 major reaction types, which will be oxidation reduction, acid-base chemistry, and precipitation reactions. The forming of solids out of 2 aqueous solutions, the changing of charge states, often changing in color and stuff, and the acid base, the neutralization of a proton with a hydroxide. But there's a few other types of reaction types we can learn about. So these are just, I'm going to give the name, what they do, and essentially the common types of this. So let's break it down. Combination. It's a pretty standard type. Combination is just 2 compounds come together to form one new compound. Could be 2 elements, could be 2 compounds, but it's 2 things come together to form one. Some of these reactions can fall under 2 different categories, depending on what's going on. But common one, zinc oxide, CO2 bind together to form zinc carbonate. So the carbon dioxide binds with the oxygen to form a carbonate, and so we have 2 compounds coming together. Sodium solid and chlorine gas form sodium chloride salt. That's another example of combination. That's also an example of an oxidation reduction, as we'll see. Another one we've done this one in lab. Magnesium plus oxygen gives you magnesium oxide. Two things came together to form one. That also would have been an oxidation reduction. That would have also been a combustion. Now, the opposite case, decomposition. One compound will break apart to form two or more, such that, like, say, hydrogen peroxide will break apart to form water and oxygen. That's also oxidation reduction. Perchlorate can be reacted to form potassium chloride and oxygen gas. That's the kind of opposite type reaction of the MgO one. But so one coming together to form two, or two falling apart to form one. We're decomposing. Now, single displacement and double displacement is what they sound like. Single displacement, we have a combination of A and BC. We have one element by itself and one compound. And basically what happens is we swap out an element. The example we gave earlier with aluminum and iron oxide goes to iron and aluminum oxide. It's like oxygen is the belle of the ball, and it's just switched dance partners. It's just swapped. I'll give aluminum a turn now that I've danced with iron. Double displacement would be a situation where we have two compounds and both compounds switch. Just like single displacement, except in this case, instead of aluminum having no partner, aluminum already has an anionic partner, and they just swap places. Had we done this in everyday chemicals, you could have done this reaction. You mix silver nitrate and, say, sodium chloride, and you would have formed silver chloride and sodium nitrate. And just we swap the cations to make different pairs. And finally, on these generic types, we have combustion. Combustion is a reaction with oxygen to form a binary oxide of some kind. So in the case of this guy's ethane would burn with oxygen to form CO2 and water. But we could also say sulfur. Sulfur can burn with oxygen to form SO2. We can say charcoal will burn to form CO2. We can say magnesium burned in oxygen to form MgO. All these guys are combustion reactions. It's basically a reaction with oxygen to form some sort of oxide. And here's the one important thing. Well, I'm going to leave you after this slide. We're going to go ahead and call it whatever. All these reactions need a driving force. There has to be something that pushes them forward. Without a driving force, a car just sits in your driveway. Without gasoline, the car's not going to move unless it's on a hill. And even if it's on a hill, it's going to move. If it has the brakes on, it's not really going to move. You need something to push it to get it going. All these guys will have some force that's going to change in energy to form a more stable state. Take the car on the hill. Maybe it's up on blocks, so it's not moving. You give it a push off that block, stopping the wheel. Suddenly the car is going to start rolling down until it gets to the low point in the ground, and it's going to stop. Now, this driving force could be a change in energy. can change in energy, which we'll talk about in the later chapters. Enthalpy, the energy of reaction. But it also could be a change in randomness or entropy, which will come about next semester. Basically, it's going to make things a little bit more crazy, chaotic. So in aqueous reactions, some of these driving forces could be like a precipitation. When we form a solid out of two solutions, that precipitation of a solid is going to force this to conclusion. An acid base. One thing that's going to force these guys to conclusion is water forming. You're going to neutralize the acid with the base. An oxidation reduction is going to be another driving force. Essentially, in precipitation reactions, we have a double displacement that forms a solid. If you can do-si-do with your partner and swap partners like that, what's going to keep it on the product side? What's going to keep it on the product side if you take your rival's partner and then go marry her all of a sudden? You leave the dance and marry her. Suddenly, she's gone. She's out of the dance. You can't come back. That's what you're doing. You're forming a solid. You're crashing out of solution. You're leaving the party. You can't swap partners back. It's going to force this to product. In a neutralization reaction, an acid mixes with a base to form water. An acid is essentially going to be like another double displacement, except instead of forming a solid, you're forming liquid water, which once again doesn't want to go back. And then in an oxidation reduction reaction, electrons end up getting transferred and you form a low energy product. These are going to be some driving forces that we're going to look at, especially in the next week. But for now, that is all I got. Stop here. We're out of time. Thank you for your attendance. Have a nice weekend.